Section 27 of the Science, History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science, History of the Universe, Volume 2, edited by Francis Rolt-Wheeler. Geology, Chapter 13, Historical Geology, Part 4. The post-tertiary or quaternary portion of the geological record includes the various superficial deposits in which nearly all the mollusca are of still living species. It is usually subdivided into two series. 1. An older group of deposits in which many of the mammals are of extinct species. To this group the names Pleistocene, Post-Pliocene, and Diluvian have been given. And 2. A latter series wherein the mammals are all, or nearly all, of still living species, to which the names recent, alluvial, and human have been assigned. These subdivisions, however, are confessedly very artificial, and it is often exceedingly difficult to draw any line between them. The gradual refrigeration of climate at the close of the Tertiary ages affected the higher latitudes alike of the Old and the New World. As the cold increased, says Geikie, the whole of the north of Europe came eventually to be buried under ice, which, filling up the basins of the Baltic and North Sea, spread over the plains even as far south as close to the site of London, and in Silesia and Galicia to the 50th parallel of latitude. Beyond the limits reached by the northern ice sheet, the climate was so arctic that snowfields and glaciers stretched even over the comparatively low hills of the Lyonnais and Beaujolais in the heart of France. The Alps were loaded with vast snowfields, from which enormous glaciers descended into the plains on either side, overriding ranges of minor hills on their way. The Pyrenees were in like manner covered, while snowfields and glaciers extended southward for some distance over the Iberian Peninsula. In North America also, Canada and the eastern states of the American Union, down to about the 40th parallel of north latitude, lay under the northern ice sheet. Owing mainly to the direction of the prevalent moisture-bearing winds, the snowfall was greatest toward the west and northwest, and in the direction of Scandinavia the ice sheets attained their greatest thickness. The Scandinavian ice joined that which spread over Britain, where the dimensions of the sheet were likewise great. Many mountains in the Scottish Highlands show marks of the ice sheet at heights of 3,000 feet and more. If to this depth be added that of the deep lakes and fjords which were filled with ice, it is evident that the sheet may have been as much as 4,000 or 5,000 feet thick in the northern parts of Britain. This vast icy covering, like the Arctic and Antarctic ice sheets of the present day, was in continual motion, slowly draining downward to lower levels. Toward the west its edge reached the sea, as in Greenland now, and must have advanced some distance along the sea floor until it broke off into bergs that floated away northward. Toward the south and east it ended off upon land and no doubt discharged copious streams of glacier water over the ground in its front. In northern Germany, Denmark, Finland, and Scandinavia, the southern limits at which the ice rested a long while before retiring are indicated by long winding ramparts of detritus, or end moraine. In North America also, the southern edge of the ice sheet is marked by similar terminal moraines, which are well displayed from Pennsylvania to Dakota. When this glaciation took place, the terrestrial surface of the northern hemisphere had acquired the main configuration which it presents today. The same ranges of hills and lines of valleys which now serve to carry off the rainfall served then to direct the results of the snowfall seaward. The snowsheds of the Ice Age probably corresponded essentially with the watersheds of the present day. Yet there is evidence that the coincidence between them was not always exact. In some cases the snow and ice accumulated to so much greater a depth on one side of a ridge than on the other, that the flow actually passed across the ridge, and the detritus was carried out of one basin into another. A remarkable instance of this kind has been observed in the north of Scotland, where so thick was the ice sheet that fragments of rock from the centre of Sutherland have been carried up westward across the main water parting of the country and have been dropped on the western side. In North America also, abundant evidence is afforded of a northern ice sheet which overrode Canada and the eastern states, southward to about the 40th parallel of latitude in the valley of the Missouri. Several centers of dispersion have been noted from which this ice moved outward, chiefly in a general southerly direction, but in the middle part the ice streamed northward into the Arctic Ocean. The great mountain ranges farther south likewise nourished the numerous valley glaciers which radiated outward from the high ground. As great oscillations of climate took place during the Ice Age, and in some cases probably lasted for a long time, the plants and animals both of land and sea could hardly fail to be seriously affected. During the cold intervals, northern forms would probably migrate southward, and in the warmer episodes, southern forms would push their way northward. The Arctic terrestrial animals include the mammoth, woolly rhinoceros, musk sheep, reindeer, Arctic fox, and lemming. The marine invertebrate fauna shared, though in a less degree, the effects of the meteorological and geographical changes. During the times of great cold, northern species found their way southward, some of them even as far as the basin of the Mediterranean. The cause of the remarkable change of climate during the late Tertiary and post-Tertiary time has given rise to much discussion, but is still without a completely satisfactory explanation. Some writers have favored the view that there has been a change in the position of the Earth's axis, or its center of gravity. Others have suggested that the Earth may have passed through hot and cold regions of space. Others again, and notably Lyell, have called in the effects of stupendous terrestrial changes in the distribution of land and sea, on the assumption that elevation of land about the poles must cool the temperature of the globe, while elevation round the equator would raise it. But the amount of geographical transformation thus involved was so great and the evidence for it appeared to be so slender that geologists generally have been reluctant to accept this explanation. In the difficulty of accounting for the phenomena by any feasible operation on the Earth itself, they by degrees accustomed themselves to the belief that the cold of the glacial period was not due to mere terrestrial changes, but was to be explained somehow as the result of cosmical causes. Among the recent attempts to deal with the problem of the Ice Age is the hypothesis proposed by Professor Chamberlain, on the basis of variations in the amount of carbon dioxide in the air. It is founded on the capacity of that gas for absorbing heat and to the effect that might be produced on the temperature of the air by even a comparatively small increase or diminution in the proportion of the gas. The suggestion is that while there is a general tendency to the diminution of that proportion, there arise from time to time conditions, such as great volcanic discharges, whereby much carbonic dioxide is supplied to the atmosphere. On this view, the glacial period would mark a time of great depletion of the gas, while the Arctic Miocene flora would indicate a time of comparative enrichment. Other geologists have turned back to the idea of geographical changes. That considerable oscillations of the relative levels of land and sea took place during the Ice Age has been clearly determined. The general result of investigation favors the opinion that the land in the early part of that period stood much higher than now over the northern regions of Europe and North America. If one accepts the conclusions drawn from the prolongation of land valleys upon the sea floor to a depth of many hundred feet, and from the distribution of dead littoral and shallow water shells down to depths of 6,000 or 8,000 feet in the North Atlantic, it can be seen that a vast area of highland would, under these conditions, have existed. This higher elevation would undoubtedly tend to lower the temperature. Some of the upraised parts of the seafloor might deflect warm ocean currents and thus still further increase the cold in the higher latitudes. But no satisfactory attempt has yet been made to trace out these changes geographically on actual evidence of their having occurred and to connect them with the phenomena of the Pleistocene period. The long succession of Pleistocene ages shaded without abrupt change of any kind into what is termed the human or recent period. The Ice Age, or Glacial Period, may indeed be said still to exist in Europe. The snowfields and glaciers have disappeared from Britain, France, the Vosges, and the Harz, but they still linger among the Pyrenees, remain in large mass among the Alps, and spread over wide areas of northern Scandinavia. This dovetailing or overlapping of geological periods has been the rule from the beginning of time, the apparently abrupt transitions in the geological record being due to imperfections in the chronicle. The human period, resumes Geikie, is above all distinguished by the presence and influence of man. It is difficult to determine how far back the limit of the period should be placed. The question has been asked whether man was coeval with the Ice Age. To give an answer, we must know within what limits the term Ice Age is used and to what particular country or district the question refers, for it is evident that even today man is contemporary with the Ice Age in the Alpine valleys and in Finland. There can be no doubt that he inhabited Europe after the greatest extension of the ice. He not improbably migrated with the animals that came from warmer climates into this continent during interglacial conditions, but that he remained when the climate again became cold enough to freeze the rivers and permit an Arctic fauna to roam far south into Europe is proved by the abundance of his flint implements in the thick river gravels, into which they no doubt often fell through holes in the ice as he was fishing. The proofs of the existence of man in former geological periods are not to be expected solely or mainly in the occurrence of his own bodily remains, as in the case of other animals. His bones are indeed now and then to be found, but in the vast majority of cases his former presence is revealed by the implements he has left behind him, formed of stone, metal, or bone. The history of the Bronze and Iron Ages in Europe is told in great fullness, but belongs more fittingly to the domain of the archaeologist, who claims as his proper field of research the history of man upon the globe. The remains from which the records of these ages is compiled are objects of human manufacture, graves, cairns, sculptured stones, etc., and their relative dates have in most cases been decided, not upon geological but upon archaeological grounds. When, however, the sequence of human relics can be shown by the order in which they have been successively entombed, the inquiry is strictly geological and the reasoning is as logical and trustworthy as in the case of any other kind of fossils. The age of the earth is another matter which geologists must needs speak of in terms of extreme guardedness. Reasoning by analogy, it is true, there is a certain standard to be secured. Thus, for example, when it is discovered that water flowing at a certain speed cuts away the particles of a certain rock so many fractions of an inch in a decade, it is assumed that where so many feet have been cut away from a certain rock by the influence of water, the proportion so cut away must represent so many multiples of the fraction of an inch cut away in a decade, and therefore the time that has been since the beginning of the cutting away of that gorge, such as Niagara, is an equivalent number of multiples of the decade of years. But while this affords an excellent basis for rough estimation, it is not to be forgotten that it acts entirely on the assumption that matter was in those early days as it is now, and that the forces are unchanged. This assumption, however useful, cannot be termed strictly scientific, for there is no means of determining whether the original groove, for example, may not have been made in the time when the rock was in a viscous state, or even so superheated that water would cause violent fractures, since worn smooth. The same holds true for sedimentation. A certain land is regarded as being so many thousands or millions of years in age because of the rate at which it has been laid down in sediment. But geologists are becoming more wary of this, especially since the discovery of some coins in a bog in Germany, which, according to the estimates of the laying down of peat, must have been 18,000 years old, and yet which were found to have the stamp of Claudius Caesar. The physical argument, moreover, that changes in plants and animals have taken a long while to produce is purely dependent upon a certain theory of variation in biology, a theory by no means certain or approved. Thus, to give the best known modern instance, in the space of 10 years, Hugo de Vries, the great Amsterdam botanist, has observed a variation in the evening primrose, which is permanent and reproductive, yet which according to the older ideas of infinitely slow variation would have been presumed to have taken hundreds if not thousands of years. More, if the forces of life were stronger in their youth, as is not an impossible assumption, changes could and probably would occur with greater variation and at higher speeds than at the present time, when the force has been worked over and over for myriad centuries. An ingenious geological argument has been based by Professor J. Joly of Trinity College, Dublin, on the quantity of sodium present in the water of the ocean as a measure of the age of the earth. He assumes that the sodium contained in that water was not derived from the primeval atmosphere or the original constitution of the ocean, but has been supplied in the long course of geological time by the denudation of the land and the consequent removal of the material in solution from the terrestrial rocks. He arrives at the conclusion that if the present annual supply be taken as a measure of what has been the rate in past time, a period of between 90 and 100 millions of years has elapsed since the ocean began to receive its tribute of chemical solution from the land. The geological argument for the age of the earth may be summed up thus. The geological evidence indicates an interval of probably not much less than 100 million years since the earliest forms of life appeared upon the earth and the oldest stratified rocks began to be laid down. The physical argument as to the age of this planet is based upon three kinds of evidence. 1. The internal heat and rate of cooling of the earth. 2. The tidal retardation of the earth's rotation. And 3. The origin and age of the sun's heat. 1. Applying Fourier's theory of thermal conductivity, Lord Kelvin pointed out as far back as the year 1862 that the superficial consolidation of the globe could not have occurred less than 20 million years ago, or the underground heat would have been greater than it is, nor more than 400 million years ago, otherwise the underground temperature would have shown no sensible increase downward. He would now restrict the time to between 20 and 40 millions. 2. The reasoning from tidal retardation proceeds on the admitted fact that owing to the friction of the tidal wave, the rotation of the earth is retarded, and is therefore slower now than it must have been at one time. Lord Kelvin contends that had the globe become solid some 10,000 million years ago, or indeed any high antiquity beyond 100 million years, the centrifugal force due to the more rapid rotation must have given the planet a very much greater polar flattening than it actually possesses. 3. The third kind of evidence leads to results similar to those derived from the two previous lines of reasoning. It is based upon calculations as to the amount of heat that would be available by the falling together of masses from space, which by their impact gave rise to our sun, and the rate at which this heat has been radiated. Assuming that the sun has been cooling at a uniform rate, Professor Tate concluded that it cannot have supplied the earth, even at the present rate, for more than 15 or 20 million years. Lord Kelvin also believes that the sun's light will not last more than 5 or 6 millions of years longer. Believing that almost anything is possible as to the present internal state of the earth, Professor Perry concluded an article in Nature in these words: "To sum up, we can find no published record of any lower maximum age of life on earth, as calculated by physicists, than 400 millions of years. From the three physical arguments, Lord Kelvin's higher limits are 1,000, 400, and 500 million years. I have shown that we have reasons for believing that the age, from all these, may be considerably underestimated. It is to be observed that if we exclude everything but the arguments from mere physics, the probable age of life on the earth is much less than any of the above estimates. But if the paleontologists have good reasons for demanding much greater time, I see nothing from the physicist's point of view which denies them 4 times the greatest of these estimates." End of section 27.